The size of the ground rod for a 200 amp service is a crucial aspect of ensuring electrical safety and compliance with the National Electrical Code, or NEC. The primary function of a ground rod is to provide a low impedance path for fault current to return to the source, thus facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This helps to minimize the risk of electrical shock and fire hazards. The NEC specifies the requirements for grounding electrodes in Article 250. The grounding electrode system must effectively connect the electrical system to the earth. This connection ensures that in the event of a fault, the ground provides a low resistance path for current to flow back to the source, causing the overcurrent protection device to trip and disconnect the power. Now, addressing the specific question of whether to use a 1/2 inch or 5/8 inch diameter ground rod for a 200 amp service, the NEC does not explicitly dictate the ground rod size based solely on the service amperage. Instead, the code focuses on meeting overall grounding impedance requirements and the material and installation specifications of the grounding electrode. However, a 5/8 inch diameter ground rod is generally preferred and often required by local jurisdictions due to its increased mechanical strength and corrosion resistance. 5/8 inch ground rod is more robust and can withstand the physical stresses of installation and soil conditions better than a 1/2 inch rod. This is particularly important in areas with rocky or corrosive soil. The NEC in Section 250.52 specifies the types of grounding electrodes that are permitted. These include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and ground rods and pipes. When using ground rods or pipes, the NEC has specific requirements for their installation and dimensions. Section 250.53G details the requirements for rod, pipe, and plate electrodes. This section stipulates that the grounding electrode must be installed such that at least 8 feet of its length is in contact with the soil. This ensures adequate contact with the earth to provide an effective grounding path. Regarding the material and dimensions of ground rods, Section 250.52 specifies that ground rods should be made of approved materials such as copper, copper-clad steel, or galvanized steel. For ground rods made of steel or iron, and this is very important, they must be at least 5/8 inch in diameter. Non-ferrous materials like copper can be smaller, usually at least 1/2 inch in diameter. The reason for this difference in required diameter is primarily due to the mechanical strength and corrosion resistance of the materials. Steel and iron are more susceptible to corrosion than copper, so a larger diameter is needed to ensure a longer service life and maintain effective grounding. Copper and copper-clad steel rods, being more corrosion resistant, can be smaller in diameter while still providing adequate grounding capability. Now, let's talk about the number of ground rods needed. The NEC generally requires that a single ground rod, if used as the sole grounding electrode, must have a resistance to ground of 25 ohms or less. If a single ground rod does not meet this resistance requirement, a second ground rod is required. The two ground rods must be spaced at least 6 feet apart. This spacing helps to reduce the overlap of their effective grounding zones and improve overall grounding effectiveness. The resistance to ground can be measured using a ground resistance tester, which is a specialized instrument designed for this purpose. This tester injects a current into the earth and measures the resulting voltage drop to calculate the resistance. In practice, many electricians and inspectors prefer to install 2 ground rods regardless of the measured resistance of a single rod. This provides an added layer of safety and redundancy, ensuring a more reliable grounding system. While the NEC doesn't explicitly mandate a 5/8 inch ground rod for a 200 amp service based solely on amperage, the combination of material requirements, mechanical strength considerations, and local code interpretations often leads to the specification of a 5/8 inch rod. It is crucial to check with local electrical codes and the authority having jurisdiction, or OJ, to confirm the specific requirements in a particular area. Local codes may have more stringent requirements than the NEC, and the AHA has the final say on what is acceptable. Now let's consider the installation process. Proper installation of ground rods is essential for ensuring their effectiveness. Firstly, the ground rod should be driven into the earth vertically until at least 8 feet of its length is in contact with the soil. If it is not possible to drive the rod vertically due to obstructions such as rocks, it can be buried at an angle not exceeding 45 degrees from vertical, or it can be buried horizontally at a depth of at least 30 inches. When driving the ground rod, care should be taken not to damage the rod or its coating. Using a ground rod driver can help to prevent damage and ensure that the rod is driven straight into the earth. Secondly, the connection between the grounding electrode conductor and the ground rod must be made with an approved connector. The connector should be listed for direct burial and made of a material compatible with both the ground rod and the grounding electrode conductor to prevent corrosion. The grounding electrode conductor is typically a copper wire that connects the ground rod to the service equipment. The size of the grounding electrode conductor is determined by an EC table 250.66, which bases the conductor size on the size of the service entrance conductors. It is important to use the correct size grounding electrode conductor to ensure that it can safely carry fault current. After making the connection, it should be protected from mechanical damage and corrosion. This can be done by burying the connection or by using a protective covering. Thirdly, it is important to ensure that the area around the ground rod is free of any obstructions that could interfere with its performance. This includes removing any vegetation or debris that could prevent the rod from making good contact with the soil. In summary, the appropriate size ground rod for a 200 amp service is generally a 5/8 inch by 8 foot ground rod, especially if it is made of steel or iron. While the NEC does not explicitly require this size based solely on amperage, the combination of material requirements, mechanical strength considerations, and local code interpretations often leads to this specification. Always check with local electrical codes and the authority having jurisdiction to confirm the specific requirements at a particular area. Proper installation of the ground rod is essential for ensuring its effectiveness. This includes driving the rod to the correct depth, using an approved connector, and protecting the connection from damage and corrosion. By following these guidelines, you can ensure that the grounding system provides adequate protection against electrical shock and fire hazards. Remember that grounding is a critical component of electrical safety, and it is essential to take it seriously. If you are not comfortable working with electricity, it is always best to hire a qualified electrician to perform the work. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Now, let's consider some additional factors that can affect the performance of a ground rod. Firstly, the soil conditions play a significant role in determining the effectiveness of the grounding system. The ideal soil for grounding is moist and conductive. Sandy or rocky soil is less conductive and may require the installation of additional ground rods to achieve the required resistance to ground. Secondly, the presence of underground utilities can affect the placement of ground rods. It is important to locate any underground utilities before driving a ground rod to avoid damaging them. Call before you dig is always a good practice to follow. Thirdly, the proximity of other grounded structures can affect the performance of a ground rod. If there are other grounded structures nearby, such as metal fences or underground pipes, they can create a parallel path for current flow, which can reduce the effectiveness of the ground rod. In these cases, it may be necessary to install additional ground rods or to bond the ground rod to the other grounded structures. Bonding is the process of connecting two or more conductive objects together to create a common electrical potential. This helps to ensure that there is no voltage difference between the objects, which can reduce the risk of electrical shock. In addition to ground rods, there are other types of grounding electrodes that can be used. These include ground plates, ground grids, and concrete encased electrodes, which are also known as UFA grounds. Ground plates are typically made of copper or galvanized steel and are buried horizontally in the earth. Ground grids are a network of interconnected conductors that are buried in the earth. Concrete encased electrodes are made of a length of bare copper conductor that is encased in concrete. The type of grounding electrode that is used will depend on the specific site conditions and the requirements of the local electrical code. In some cases, it may be necessary to use a combination of different types of grounding electrodes to achieve the required grounding performance. For example, a ground rod may be used in conjunction with a concrete encased electrode to provide a more effective grounding system. It is important to consult with a qualified electrician or engineer to determine the best type of grounding electrode for a particular application. Now let's delve a bit deeper into the NEC requirements for grounding electrode conductors. The grounding electrode conductor is the conductor that connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined by NEC Table 250.66, which bases the conductor size on the size of the service entrance conductors. For example, if the service entrance conductors are 2/0 copper or 4/0 aluminum, the grounding electrode conductor must be at least a number 4 copper wire. It is important to note that the grounding electrode conductor must be installed in a manner that protects it from physical damage. This can be done by running the conductor in conduit or by using a cable assembly that is listed for direct burial. The grounding electrode conductor must also be connected to the grounding electrode using an approved connector. The connector should be listed for direct burial and made of a material that is compatible with both the grounding electrode conductor and the grounding electrode. Now let's discuss the importance of proper bonding. Bonding is the process of connecting two or more conductive objects together to create a common electrical potential. This helps to ensure that there is no voltage difference between the objects, which can reduce the risk of electrical shock. The NEC requires that all metal parts of an electrical system be bonded together, including metal enclosures, metal conduit, and metal equipment. This bonding is typically accomplished using bonding jumpers, which are short lengths of copper wire that are used to connect the metal parts together. The bonding jumpers must be sized according to NEC Table 250.102, which bases the jumper size on the size of the circuit conductors. It is important to ensure that all bonding jumpers are properly installed and tightened to ensure a good electrical connection. In addition to bonding the metal parts of an electrical system, it is also important to bond the non-current carrying metal parts of equipment to the grounding system. This includes the metal frames of appliances, the metal housings of motors, and the metal enclosures of electrical panels. This bonding helps to ensure that if a fault occurs, the fault current will flow back to the source, causing the overcurrent protection device to trip and disconnect the power. The NEC requires that all equipment grounding conductors be connected to the equipment grounding bus in the electrical panel. The equipment grounding bus is a metal bar that is connected to the grounding electrode conductor. This provides a path for fault current to flow back to the source. Now let's talk about the importance of ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit and detecting any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI will trip and disconnect the power. GFCIs are required in many areas of the home, including bathrooms, kitchens, and outdoor locations. They are also required on construction sites and in other hazardous locations. It is important to test GFCIs regularly to ensure that they are working properly. This can be done by pressing the test button on the GFCI. If the GFCI does not trip, it should be replaced. In conclusion, the grounding system is a critical component of electrical safety. It is important to ensure that the grounding system is properly designed, installed, and maintained to protect people from electrical shock and fire hazards. Always consult with a qualified electrician or engineer to ensure that the grounding system meets the requirements of the NEC and local electrical codes. Remember that electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others.